2:30 here. However, at 2:15, there will be picture taking outside this room.
Wait, how bad an accident?
I wasn't told.
It's not a car accident, it's a previous accident.
He had it
Oh.
6 months ago, he hurt his back.
I'm thinking.
Putting it on a plane.
Who is this here? Oh, just
In
now.
the right.
Just now. Oh. All right. Thank you. Okay. Welcome to the secondary session. The first talk is going to be by Jim Marshall, and he's going to be covering some of the cognitive science books.
Okay, thank you. Hello, everybody. It's really fun to be back at IU. I'd like to thank Julia for inviting me to this conference. I want to tell you about a course that I developed at Pomona where I am. But before I do that, I want to mention a few things about Dan at the beginning here. I was trying to reflect on vignettes that I think of when I think of Dan. And to me, there are a lot of reasons why I admire Dan very much. One of them is he's always had this certain irrepressible joviality, sense of humor about him that I've always really enjoyed. And also his teaching and his research and the rest of his life have always been just bound up together. It's one and the same. And I thought of a couple of things that I might mention, just sort of that summarizes this in my own mind. How many people here know that his dog, Misty, for a while was listed in the Bloomington phone book as Misty Friedman? I discovered that by accident one day. That was pretty funny. There's another thing that I remember from my grad school days and being the AI for 311, or just 511 or 311, for many semesters. Dan used to ask his grad students from time to time to house sit. And he asked me to house sit one weekend, and since I was, of course, starving grad student, so I was more than happy to give up my grad student hovel for a couple of days and move into his house. And I remember something that, it's a little thing, but to me it really sums up in a nutshell the way that he integrates his teaching and his research with his life and a sense of humor. This is back in the days when 611, which I took, was in the morning. We would meet at Dan's office. And I don't remember when I was house sitting when I was actually teaching. I was taking 611, but I think I had at that point. And anyway, I was house sitting, and it was time to go to bed, and I went to the alarm clock because I was going to set the alarm, and I discovered that it was set for 6:11. And I thought, this is great. The alarm is set for 6:11. So I thought that was hilarious. So anyway, I just wanted to share that with you. I don't know if was that actually intentional, Dan? You remember?
You'll never get it out of me.
All right. Well, it can't have been intentional. I mean, it cannot have been intentional. All right. So I want to tell you a little bit about this course at Pomona. Pomona is a small liberal arts college in California, and it's unusual in the sense that we actually do have a cognitive science major for undergraduates administered by the Department of Linguistics and Cognitive Science. Not too many liberal arts colleges have, although I think that's increasing. Hopefully it will continue to increase. We didn't have any computer science courses required for the cognitive science major. It's a new major. It's been around for the past couple of years. And that was partly because there were no appropriate introductory CS courses for cognitive science students. So I've been at Pomona for 3 or 4 years now, and involved in the development of this cognitive science program. So we thought we really need to address this deficiency. We need to come up with a course for non-CS majors, cognitive science majors, that would give people a flavor of what computer science and computation is all about. Because, I mean, it's really ironic, if you think about it, to be a cognitive science major and never take a computer science course, since computation is so central to the notion of cognitive science. So we introduced this course, I designed and taught it for the first time in fall of 2002, called it computation and cognition to try to fill this gap. So I want to just briefly go through and tell you what we did, or what I did, and some of the objectives of the course. So there were several objectives. We wanted this to be aimed at students with backgrounds in linguistics, philosophy, psychology, neuroscience, not CS majors or potential majors. And because the Cog-Sci major has a lot of requirements from various departments, we knew that this would really be the only computer science course that cognitive science students would be able to take. So I wanted to make this as self-contained and comprehensive as possible. I wanted to really get across what is computation and why is it central to Cog-Sci. But there were some challenges. Most of the students were not going to have very much technical programming background, so I couldn't really expect that they had done any programming experience. So the main goals were, I wanted the students at the end of the day to understand this notion of computation, why it's central to cognitive science. And it seemed to me that the only way to really do that is to get your hands dirty and learn how to program. And I wanted ultimately the students to be able to implement some simple models, simple computational models of cognition, learning, memory, perception, and so on, and to be able to experiment around with a little bit, just so they understand from a first-hand point of view what it means to model something computationally. And also I wanted to make sure that they understood what a Turing machine was. That was actually an explicit request by one of the philosophers. He wanted them, the students coming out of CS30, to know what a Turing machine was. And obviously, yes, the philosopher did. But
why do you think it was important?
Well, I mean, Turing machines, philosophy has lots of arguments that center around Turing machines, and we just wanted somebody who calls themselves a cognitive science major to be able to have an intelligent conversation about a Turing machine and the idea of computation in the abstract. All right, so these are some of the big questions that I hope this course would address. What is computation and why is it important to cognitive science? I wanted to get across this distinction between symbolic, so-called top-down symbolic models, which is sort of the classical AI approach. Not that I think that's the best approach, but I think it's worthwhile. If you're going to denigrate one approach, you might as well understand what you're denigrating. And also I wanted to get across the idea of emergence, bottom-up emergent models of cognition. How do they differ? Also very important is to understand the limits of computation in principle and what these limits might imply, if anything, about human or machine intelligence. And also what is this notion of embodied cognitive science? So the idea that you need to have some kind of physical interaction with your environment in order to understand intelligence. All right, so I'm going to go through very quickly the synopsis of the course here, just give you a sense of the topics that we covered and the readings that we did. I didn't want this to be just a straight programming course, although that was a large component of it. I wanted definitely to read some important papers at an accessible level and have the students discuss them in class and write reactions to them. So I chose Scheme, of course, my favorite language, but not just because it was my favorite language. I think it's a very good pedagogical language. I'm sure I don't have to convince anybody in this room. We used the textbooks The Little Schemer by everybody knows. Concrete Abstractions was the other textbook, which is sort of a more, I'm not sure if I want to say accessible, but a less intense version of probably my favorite textbook of all time, Structure and Interpretation of Computer Programs, or at least one of the top 3 or 4. So those were the Scheme books that we used. And the course was structured as 2 lectures and 1 closed lab session every week in a computer classroom, which was important, I think, because every time I introduced a programming concept, I wanted to be able to reinforce that immediately by having the students do some kind of little exercise. Another nice thing about Scheme is that it's interactive, it's interpretive, so it's very easy. You don't have to compile anything, you just type at the prompt. So it gives students immediate feedback. So we started out the first month of the course as basically CS1 with a functional twist, a functional flavored CS1. So there wasn't a whole lot about cognitive science in the first month. I was really just trying to get the students up to speed with programming so that then we could do interesting things later on. So we focused a lot on list manipulation, lists and symbol manipulation, recursion, data abstraction, recursion, Did I mention recursion? And so on. I like recursion too. All right, then after I felt like they had come up to speed with programming enough, then we could get to the fun stuff. So I had them read Turing's classic article, Computing Machinery and Intelligence, and also a nice Scientific American article by Doug Hofstadter on the Turing test. And that was the basis for our class discussions on the Turing test. And I had them write reactions to these readings and I posted them on our webpage so that students could see what the other students had thought and written. And this discussion served as the background for one of the more involved programming assignments, which I took from a section in Concrete Abstractions. It's actually one of the reasons why I decided to go with that book. There's a nice extended exercise in that book where students developed this very simple natural language interface to a movie database using your typical list processing scheme type approach. So that was intended to get across the flavor of traditional symbolic models of AI, or of intelligence, that it dominated, at least did dominate the early years of AI for so long. So that was sort of the first larger scale programming assignment. And that served a couple of purposes. One, by reading and discussing Turing's article, which, as everybody I'm sure knows, it has all kinds of fascinating discussions about lots of different topics, not just the mind. Turing was such a visionary. He really was able to foresee a lot of the developments in AI over the next 40 or 50 years. He wrote that article in 1950. And so it mentions the idea of Turing machines and universal computation. So by having already read Turing's article, that sort of set the stage for our next topic in the course, which was Turing machines and computability. I also included a chapter from John Casty's book, Searching for Certainty. The chapter is called Proof or Consequences, as background reading. It was just about the right level to introduce the ideas of computability and Turing machines to a non-technical audience. But that was a nice supplementary reading. And from there, we talked about the halting problem. And another beautiful thing about Scheme is that it's so easy to prove the halting problem in Scheme. I mean, conceptually, the proof, the gist of the idea is expressible, in just a few lines. So that was very nice. So we talked about the limits of computation that way, the Church-Turing thesis, the idea of universality of computation, that you can have machines mimicking other machines all you want. From there, the next assignment involved developing a Turing machine simulator in Scheme, which itself illustrated this idea of universal computation. We had our little Scheme program for one machine simulating another Turing machine. Basically, it was a little interpreter. So I got a little bit of the flavor of 311 in my course on a very small scale, because this Scheme Turing machine simulator took in symbolic descriptions of Turing machines and interpreted them. So that was nice. And then as a lab exercise, I had the students use our simulator to play around with Busy Beaver Turing machines that are very simple to describe with a few number of states that have very, very complicated behavior. Some of these little 5-state machines that we played around with ran for like 10 or 20 million steps. So it was fun for them to see that you can have a very concise, simple description of something, and it turns out that the behavior described by those rules is extremely complex. So that was one of the morals that I wanted to get across. The other moral, sort of the flip side, was that behavior that may appear to be complex or purposeful doesn't necessarily have to be. It doesn't have to be based on complex mechanisms. Maybe it is, maybe it's not. All right. So then, now that the students had actually acquired some experience with symbolic programming and Scheme, they were in a position to understand some of the other debates in AI. Newell and Simon's physical symbol system hypothesis. I had them read the Computer Sciences Empirical Inquiry paper where they laid out this hypothesis. I also had them read John Searle's paper, Mind, Brains, and Programs, about the Chinese Room as a nice counterpoint. Also another wonderful piece by Doug conversation with Einstein's brain that gave some nice perspective on this debate. But I really felt like now that students had gotten their hands dirty with scheme programming, they knew what it meant to talk about a symbol and meaning in a way that I think they wouldn't have if they hadn't actually done the programming. Okay, so that sort of finished up the symbolic component of the course. Then we turned our attention to emergent models of cognition. I'm very interested in neural networks and the idea of collective computation. So we read The Appeal of Parallel Distributed Processing, Chapter 1 of this classic 2-volume set of books in the neural network field that talked about neural network models of learning and memory. Unfortunately, I didn't really have enough time to do this right. We talked about one-layer networks and how to train pattern associator networks a little bit. We talked about a neural network model of memory that was discussed, actually it was done by Jay McClellan and discussed in this reading. So another homework assignment was to implement this Jets and Sharks neural network interactive activation model of memory and play around with that. So I got object-oriented programming in the usual scheme style, and it was really pretty easy to do. That took a couple of weeks. And so the students were able to learn a little bit about object-oriented programming and neural network models of memory, and they could play around with the effects of changing the parameters in the memory and so on. I didn't have time for more sophisticated models of learning like the multi-layer network backpropagation algorithm. Maybe next time. And then we finished up with the idea of embodied cognitive science. This idea that intelligence depends critically on the interaction of a physical system with the environment. So you can't just subtract out the environment, and you need to somehow incorporate the environment, the effects of the environment on your physical system. At least this is one large school of thought in cognitive science. So we read a few chapters from Valentino Bradenberg's book, Vehicles, wonderful little book if you haven't read it. And we used Handyboard and Lego robots to implement some of the Bradenberg vehicles described in the book. Unfortunately, we had to use the interactive C programming language, so we had to switch gears. I couldn't use Scheme, so that was a little rocky, but actually it wasn't too bad. My students managed to deal with it. But it would have been nicer not to have to shift gears and talk about interactive C explicitly. We also talked about some of Rod Brooks's work on behavior-based robotics, subsumption architecture, and we read one of his papers about the subsumption architecture, intelligence without representation, which is a little more philosophical and less technical. All right, and so there was one theme that I was sort of proud of myself for weaving together in several different ways. Bradenberg in his book, in his book he talks about this law of uphill analysis and downhill invention, by which he means synthesizing complex behaviors from simple mechanisms is easier than doing the reverse, trying to infer mechanisms just based on some observed behaviors. Okay, and the students saw that firsthand in playing around with the robots, the Bradenberg vehicles. They also saw that in playing with the Busy Beaver Turing machines, and also the idea of neural networks when they were playing with their memory model. Often by cutting a few links in the memory model, you could actually change the behavior in very interesting ways, in unpredictable ways. So if anybody's interested, all my material is online. I encourage you to use it if you want. My labs are there. If you want to adapt it to your own purposes, that would be great. And I think that's it. So thank you. Any questions?
Phil wrote Kyoto Common Lisp produced a scheme for the RCX. Did you know that?
Well, I do know that there are schemes out there for RCX, and I think even Handyboard, but I haven't used them myself, and I didn't have time to actually play around with them. But that would be definitely an improvement here. Yeah.
So I really enjoyed your description of the course, but so since Matthias for license not here, somebody has to be obnoxious and play as well.
Okay.
It feels to me like this is what I would call a sort of, what my colleagues in my department would call a very old style AI course. And modern AI is so heavily statistical. I wonder how that plays into the course design.
Well, it's true that there has been...
It seems like that's the hammer with which they're trying to hit every nail right now.
Yeah, I guess I would agree with that. The probability seems to be everywhere in artificial intelligence. I mean, I wasn't really trying to make this an AI course, and I'm not sure if I think the probabilistic approach is the best way to go in AI. But I did want to give them definitely some flavor of what I would call new AI, and I think I did in the sense of talking about the embodied stuff and the bottom-up emergent models. I mean, I didn't want to just focus on old-style symbolic AI, and I don't think I did. But I didn't really talk about the probabilistic approach.
Not being one to be opinionated, what did people think about the Chinese room example?
I'm so embarrassed to say I actually had some students who were convinced by it, and I couldn't unconvince them. I didn't do my job, I guess.
How did Searle get tenure?
He had tenure already.
Okay, anybody else? All right, thank you.